All right, and we talked a little bit about the graph of a quadratic, but like we talked about before, it's called a parabola. So it's a U-shaped curve, and and you can see there's different real life applications of parabolas, and so yeah, it's something that we'll see a fair amount and use a lot. Like even into calculus, you'll use quadratics to model different types of situations. So you can see here they talk about satellite dishes and flashlight reflectors. So, but yeah, there's definitely more applications than that. So when we look at the graph of a quadratic function, basically some of the features that we have, like some of the anatomy of a parabola or quadratic, is that you have a vertex. So the vertex is the point, kind of at the tip of the U or the parabola shape, right? So it's the low point if it's an upward facing parabola, and it's the high point if it's a downward facing parabola. So that's what the vertex is it's remember we talked about extrema, and so the vertex is the extreme point of a parabola, whether it's the minimum, again, if it opens upwards, or if it's the maximum, if a parabola opens downward. Okay. Now remember we talked about the leading coefficient being important. So A tells you whether the parabola is facing up or down, right? So if A is positive, if A is positive, that means you have an upward facing parabola. If you have a negative A, that means it's a downward facing parabola, right? And that's what this means, right? Positive A is greater than 0, that's positive. A is less than 0, that's negative, okay? So that's what that's saying. All right. Now another component of a parabola is called the axis of symmetry, and so that's basically the line the line with which the parabola is symmetrical. Okay. So if you were to spin the parabola around, it would mirror, like this side mirrors this side, right? And so same thing here. This side mirrors this side. So remember, the parent function of a parabola is symmetrical about the y-axis, and so the y-axis is the axis of symmetry for the parent function of a quadratic when it's just x squared by itself. But as soon as you start transforming it and moving it, to the left or to the right or whatever the case is, then of course it's not going to be symmetrical about the y-axis, but it will be symmetrical about its own axis of symmetry. Okay, so the axis of symmetry is the vertical line that goes through the vertex. Okay, and it doesn't say it here, but the axis of symmetry would always be x equals whatever the x coordinate of the vertex is. And the vertex, we usually use h and k. If you notice, that's the same as the center of a circle, right? The same two letters we use for that. And those will come up a lot in different things, but so x equals h would be the equation of the axis of symmetry. So whatever h is, the x coordinate of the vertex, that is going to be what we set x equal to get the vertical line that goes through the vertex of a parabola. All right, so we'll go through a few just kind of basic alterations or transformations of the parent function. So we saw earlier, like the original parent function, right? Y equals x squared, or f of x equals x squared, which looks very similar to this, right? So it's the vertex is on the origin, and it's facing upward, right? And when x equals 1, y equals 1, right? Because we just square 1. When x equals 2, y equals 4 up here, right? And so forth. And so so this is basically the parent function. And so we can see if a is positive, if the leading coefficient is positive, or the number in front of x squared is positive, then it's going to be facing upward, right? And if a is greater than 1, it's going to stretch it vertically, so it's going to look thinner, right? Because it's going to stretch vertically. Or if a is between 0 and 1, if a is a fraction, it's going to compress it vertically, right? So remember that it compresses around the origin, and so it's not going to, when you press it down, or when you compress it vertically, it's not going to go down. It's just going to go towards the origin on both sides, and since there's nothing on the bottom, it'll just flatten towards the origin on top. Okay, if a is less than between 0 and 1, right? Okay, now here we see a is negative, so if a is negative, then it flips upside down, right? And the same thing, you could still have a vertical stretch or compression. A compression would look like this, and a stretch would look like this, right? It would be, it would stretch it, and so it'd be a little narrower. Okay, and so yeah, the leading coefficient being positive or negative tells you if it's facing up if it's positive and down if it's negative. So here you can see a better representation of if you have a vertical stretch, right? So two as your coefficient, since that's bigger than 1, it's going to stretch it vertically, right? Remember, since it's on the outside, it's going to be a vertical change. If you have a number like 1/3 here, then it's going to compress it vertically, right? So you can see it getting a little shallower and kind of pressing down towards the origin, right? That's what it'll look like. All right, here you have a couple translations. So here we have a vertical shift up by 1, right? So you can see it went up 1, and you can see we have a reflection about the x-axis, so it's upside down as well, right? And so remember that leading coefficient, that's what it is. There's a reflection across the x-axis, so that's what flips it upside down. And so this is, reflection across the x-axis and a shift up 1 vertically, obviously. So you can see that's what this looks like compared to the parent function there. Here on this side, you can see we have a couple transformations, and these are both translations. So we're going left 2, right, because that's inside, so it's going to be horizontal. So we went left 2 units and then down 3, right? So you can see that that's where we end up. So this was a rigid transformation, right? We didn't change the shape. There was no sizing change, just the translations, right? So whereas on the previous page we saw some sizing changes, right, which were non-rigid. So just to kind of bring those terms back up and help you to remember those. All right, so here's I referenced this earlier. So this is what the book calls standard form of a quadratic. This right here. I'm gonna call that vertex form, okay? And so so standard form for me is the one that we saw earlier, which is y equals ax squared plus bx plus c. That's what I've always known as standard form, and I feel like that's fairly universal besides this particular book, but maybe I'm wrong. So, but we'll go with that just to differentiate, because I feel like you'll see in the notes that we use vertex form for this one, and so I'm just going to call the other one standard form. So, all right, but the reason this is called vertex form is because it explicitly shows you the vertex. You have h and k. If you get it in this format, you can see what the vertex is. So h and k are the coordinates of the vertex, and so you can see that that's the vertex. H is the x coordinate and k is the y coordinate. Now remember, we use those with a circle as well. Remember, h was similar to this, how it was x minus h quantity squared. But for parabola, you don't have the y minus k part. So k is actually positive. So h is always opposite of what you think, and k is always exactly what it is. And so so just remember that when you see h in here, it's the opposite, right? But when you see k out here, it's exactly what it is, what you see it as. All right, and then the same thing with a. It's still the leading coefficient, and it still tells you whether it opens. If it's positive, it opens upward, and if a is negative, it opens downward. Okay, so this vertex form is nice because it shows you explicitly what the vertex is, and it shows you if it's facing up or down. Okay. Now what you don't get with this is the y-intercept, right? Remember, with standard form, c is your y-intercept. With this one, you don't see the y-intercept explicitly, so you'd have to actually plug in 0 for x and kind of work it out. So it's kind of helpful in different ways, right? Both are helpful in different ways. All right, so here's an example of a graph that is in vertex form. Okay, so you have this form right here, and so if we didn't see this graph here, we could look at the vertex just by looking at this, right? So we'd our h here would be -2, right? So you always get the opposite, and then this would be our k, right, as it is. And so we could plot our vertex, which would be -2, -1, right? So this is called the vertex. We'll call it capital V. And so that's where this comes from, right? And then we can see it's A is on the outside is positive 2. And so that means it's going to be facing up, right? So since this is positive, that means it's going to be up as opposed to down. And we can also see it's a vertical stretch by a factor of 2 if that's 2. So it's a little narrower than the original by a factor of 2. And yeah, and so anyway, so then we could just graph it up. Again, like I told you before, whatever h is, the axis of symmetry is always x equals that, right? Remember, for you to take make an equation of a line, it has to be an equation. So it's not just -2, it's x equals -2 is the axis of symmetry, okay? So x equals h is always your axis of symmetry, and here you can see that if h is -2, then your vertical line would go through -2 on the x-axis, right? And so that's the equation of our axis of symmetry.